Welcome, curious minds, to another deep dive.
Hi there.
Today, we're setting our sights on, well, a really long-standing challenge in industrial chemistry.
Hmm.
Our mission to unpack a truly transformative scientific breakthrough, one that promises to reshape how we approach an incredibly energy-intensive process.
It's quite exciting stuff.
It really is. So let's set the scene a bit. Imagine a crucial industrial process.
Right.
One that, for decades, has demanded extreme heat.
Yeah, really extreme.
We're talking temperatures north of 600 degrees Celsius. Just think about the hurdles that create.
Oh, absolutely. It's not just the energy cost, which is huge.
Right, massive energy costs. But it's also, it's a bottleneck. It limits sustainable scaling, adds a lot to industrial carbon footprint.
And it's tough on the equipment, the reactors, the catalysts.
Exactly. So we're specifically diving into the conversion of propane into propylene.
Propylene, yeah, a key building block.
Absolutely vital for, well, countless products we use every day, but its traditional production method, propane dehydrogenation, or PDH,
PDH.
it's always faced these major hurdles. Those intense temperatures mean, like we said, immense energy usage and degradation of the catalyst through something called sintering.
Basically, the catalyst particles clumping together, losing effectiveness.
Right. And also the formation of carbon deposits. Coke.
Yeah, coking up the catalyst.
Ugh.
Always a problem at high temps.
So it's been this stubborn, persistent challenge in chemistry and catalysis for a long, long time.
Indeed. And for decades, scientists have been, intensely searching for solutions, ways to do this exact process at much, much lower temperatures.
What was the dream target, really?
Well, the ideal, sort of the holy grail for many researchers, has been to see it happen near room temperature.
Wow, okay.
For a long time, it felt like a very distant dream in the lab, not really feasible.
Well, prepare to have that dream feel a lot closer, because a groundbreaking study has just offered an incredibly promising solution to this very challenge.
Yeah, it's generating quite a buzz.
And we're about to explore how a team of researchers has found a way to, well, basically achieve that near room temperature goal.
Flip the whole process on its head, almost.
Okay, let's get into the specifics then. This remarkable breakthrough, it's outlined in a new study published in Nature Chemistry. Pretty prestigious journal.
Definitely.
And the lead researchers we should mention, Professor Tao Zhang and Professor Aiken Wang from the Dalian Institute of Chemical Physics at the Chinese Academy of Sciences.
Right, DICP. A major center for catalysis research.
In collaboration with Professor Guy's team at the Shanghai Advanced Research Institute, also part of CAS.
So, what's truly intriguing here, the core of their novel approach. It's a water-assisted PDH process.
Water-assisted, okay.
And they use a very specific type of catalyst, a copper single-atom catalyst, an
Single atoms. So highly dispersed copper.
Exactly. But the real innovation, I think, lies in how they energize the reaction. It's driven by what they call photothermocatalysis.
Phototherma, so light and heat combined.
Precisely. But, crucially, modest heat. It uses both light and some warmth. And this is just a fundamental departure from traditional methods that rely almost entirely on sheer brute force high heat.
Okay, so what kind of temperature reduction are we talking about? You said modest heat.
Well, get this. From over 600 degrees Celsius
Yeah, the whole thing.
down to just 50 to 80 degrees Celsius.
50 to 80? Serious?
Seriously. That's what we mean by near ambient conditions.
That's astonishing. It's not just a drop. It fundamentally changes the economics, the environmental impact, everything.
It really does. For a chemical that's vital to plastics, pharmaceuticals, so many sectors.
So how did they set this up? What were the specifics?
Right, so they employed a specific catalyst that was a C1 TiO₂ SAC, copper single atoms on a titanium dioxide support,
Okay.
and they performed the reaction in a continuous flow fixed bed reactor. Pretty standard setup in one sense.
But the conditions were key.
Exactly. Within a water vapor atmosphere, that water is crucial. And this setup let them achieve that incredible temperature reduction.
While still being efficient, because sometimes low temp means slow reaction.
That's the other remarkable part. They maintained a highly impressive maximum reaction rate, 1,201 micromoles per gram of catalyst per hour.
Okay, that sounds technically impressive. What does it mean practically?
It means it works well enough, fast enough to suggest this isn't just a lab curiosity. It could be a genuinely viable, efficient industrial process, especially given those vastly lower temperatures.
Right. Which brings us to the big question, how? How did they manage this dramatic temperature drop without killing the reaction speed? What's the actual science making this work?
Okay, so they dug into the mechanism, the how, and they found three key things working together. those copper single atoms, the water vapor, and the light illumination.
The photo part of photothermo?
Exactly. Here's the sequence, basically. First, you get photocatalytic water splitting happening on the surface of that C1TiO₂ catalyst when the light hits it,
Okay, light splits water.
generating hydrogen and, importantly, hydroxyl species, OH radicals.
Reactive things.
Very reactive. Crucially, these hydroxyl radicals then adsorb. They stick onto the catalyst surface, right near the copper atoms,
Okay, so they're sitting there ready.
ready to do the work. Once adsorbed, these hydroxyl radicals directly abstract or pull off hydrogen atoms from the propane molecules flowing past.
Ah, so they're directly attacking the propane.
Directly.
Okay.
And that's the step that forms the propylene product. And interestingly, it also produces water again.
Produces water, so the water isn't used up.
Exactly. That's what's so clever. Water acts catalytically here. It participates in the reaction cycle, but it's regenerated at the end. It's not consumed.
Wow.
And this whole mechanism, using light to generate these hydroxyls, which then dehydrogenate the propane, it's fundamentally different from traditional high-heat PDH.
And also different from other methods, like using oxygen.
Right, different from oxidative dehydrogenation too, which uses oxygen and often has selectivity issues. This is a distinct water-assisted photocatalytic route.
That's fascinating for making propylene. But I'm wondering, does this clever approach have legs? Can it work for other reactions, or is it just a propane thing?
Excellent question. And yeah, the researchers definitely thought about that. They didn't stop at propane.
Good.
They went on to show that this new route could indeed be extended. They successfully applied it to dehydrogenate other light alkanes. Specifically, they showed it works for ethane and butane as well.
Okay, so it's a more general principle.
It seems to be.
Mm-hmm.
But here's maybe the most exciting part for the future.
Go on.
They found the reaction could even be directly driven by sunlight, using the same C1TiO₂ catalyst.
Sunlight, not just lab lamps.
Actual sunlight,
Yeah.
which, really opens the door to thinking about truly sustainable chemical production using the sun's energy directly.
Moving away from burning fossil fuels just to provide the heat for these reactions.
Precisely.
This really does feel like a major step change. And one of the corresponding authors, Professor Jialian Liu, put it really well. She said, and I'm quoting here, "Our study not only provides a new way for PDH, but also establishes a paradigm for conducting high-temperature reactions driven by solar energy."
Establishes a paradigm. That's a strong phrase.
It really is. It's not just a new method. It's suggesting a whole new way of thinking about these difficult chemical transformations.
Absolutely. It represents, I think, a genuine aha moment, because it signals this massive shift away from needing enormous amounts of thermal energy with all the environmental baggage that carries,
Right.
towards processes that are low energy, highly efficient, and now, potentially, directly solar-driven.
Imagine the ripple effects.
Well, yeah, it's not just cleaner propylene. It could mean cheaper plastics down the line. Maybe new bio-derived chemicals become economically viable if you don't need that huge energy input.
Or even smaller, more localized chemical plants. Less need for massive centralized facilities.
Potentially. It's a fundamental rethinking, really, of how we make some of our most vital chemical building blocks.
Yeah.
A greener, smarter way.
And there you have it, a cleaner, much more energy-efficient way to produce these vital industrial chemicals, potentially powered directly by the sun and remarkably assisted by water.
It really is a potential game changer.
It feels like it. So here's a final thought for you, our listener, to consider. Imagine a future where many of these really energy-hungry chemical reactions we rely on today, the ones needing those blast furnaces, essentially, could instead happen near room temperature, fueled just by sunlight and water. What new possibilities does that really open up? For manufacturing, sure, but also for how we manage resources for global energy solutions.
It's a big picture question.
It is. So definitely keep an eye on developments in green chemistry and catalysis, because the future is, well, it's looking potentially a lot brighter and maybe a lot cooler.